Okay, so these are quite important Banach spaces, and their definition is much more involved than the other definitions that we have seen before. And they need a good amount of measure theory, but we're going to give as much as possible. So first of all, we start with what is known as a measure space. So what is a measure space? So X is simply a set. Simply speaking, before we give the precise definition, a measure space is a space on which we can carry out integration. That's what it is. A is a family of sets of X. That has some nice properties. It's called the sigma algebra. And this pretty much means a few things. It means that X belongs to A. It also means that if A is a subset in this family, then its complement is also in the family. And it also means that if we have countably many elements of this family, then their union belongs to the family. We usually call these sets measurable. So the elements of A are called measurable sets. And mu is what measures the set. So it's a function from A with values in 0, infinity. So infinity is allowed. And we have that pretty much the empty set, which notice it's part of our sigma algebra, since X belongs to the sigma algebra and the complement of every set belongs to the sigma algebra. So the complement of the whole thing will be the empty set. So the empty set is 0. And if A1, A2, and so on belong to A and are pairwise disjoint, then the measure of their union is the sum of the measures. Okay, then if we have this, then we call this a measure. And having a set, a sigma algebra of subsets and a measure on that sigma algebra, this is usually known as a measure space. So initially what one does is one starts with f from x to 0 infinity, even the infinite value is allowed, but let's say for the moment being that we don't do that. Actually, we could include it, but it's okay if we don't. Sorry about this. And it's called measurable if the inverse image of every open set is in A. If that's true, then one can define in an unambiguous way the integral of f with respect to the measure m on x. And this ends up being a number which can be allowed to be an infinite number. And pretty much what we do is we define LP of x, comma I, comma mu. Sometimes you will see this as being denoted by either LP of x, comma A, or even LP of mu, because once you have mu, somehow the presence of x and A are presupposed. So you can find all these notations. The bottom line is that you have all functions from x to r that are measurable, and their pth power of their absolute value is integrable. And here there is another detail that if you think about it, you would never be able to build a norm like this if you have non-zero functions that have zero integral, which is possible if in most setups. So here we don't really think of functions, we actually think of equivalence class of functions. That's why I will put this, where two functions that differ on a set of measure zero are identified. So to be more precise, we don't deal with mere functions, we deal with equivalence class of functions. However, if we try to think of the elements of this space as equivalence classes, that would completely would be completely confusing. So we still think of them as functions. We just do not try to think of individual values, which make no sense since in many cases these functions are not going to have a definite value anywhere. But we can very often work with a specific function from this class of functions that are identified. So in any case, the pth norm is the integral on x of the pth power of f. And we also need to take the pth root. And it can be shown that this is a norm. Actually, showing that this norm is not that hard, but again, it has to do with properties of measure spaces and measurable functions that we're not going to go into. And that it's actually a Banach space. What is interesting is that many, even the LP spaces can be considered as special cases of this. So the LP space of all sequences whose sum of pth power converges is a special case of this. Here, f, so x will be the set of natural numbers. A will be just the power set of n, so any set is measurable, and mu is the counting measure. So it assigns to any subset of n the number of its elements. Of course, if it's an infinite subset, then it assigns the number, or it assigns the quantity infinity. So the LP space is pretty much the discussion of the LP spaces is included in the discussion of the LP spaces. And that's the amount of details that we would like to give for this particular example. And that's all. Thanks for watching.